Hello dear students, today we will discuss about the planetary motions. That is, in last class we have studied satellites, types of satellites, how it will be launched. These all are we have discussed. So next, the extension part of the same topic only, or it is in the chapter gravitation only, that is planetary motion. So this is very important and it is very interesting topic also. As we move towards the history of this planetary motions, there are many countries were given the more interesting or more curiosity topic, that is our planets and stars or a satellite celestial object, we will say that object or a planets. They are in motion. So if you observe the stars in the sky, they are said to be it is in a stationary. They are fixed there. They are shining. So they have again got the interest and recognize that something is there, and they have moved towards the further step, that is planets. Planets are not stationary, they are in a motion. The very interesting topic that the planets, they are in motion. They got the interest towards that, how it is going on, what is going on there in the sky. Planets are revolving, they are not stationary. Stars are revolving, they are not stationary. Like that, they got the interest that many countries they have approached so much interesting, that is planets are in motion, that is planetary motion concept they have got it. But later on, many scientists they have approached to study about how the planets is taking the path there, why it is not seems to be as a fixed as we observe the planets or stars, whatever we are observing from the surface of the earth, we feel it as it is a stationary, it is a fixed. We are observing from the surface of the earth. Stars are stationary and planets are stationary. We will feel it at. But they have started studying over that. So they are not stationary. They are not seems to be as a fixed there in their position. They are fixed in their position, years together. They got a concept there. They are not fixed. They are changing their position. So how it is possible, how they are taking the path, or how they are taking the motion. These all are interesting topic they have created and they have started recognizing over here. The observation, they have started observing how planets are evolving, how the stars are evolving, why they are not in a stationary position, why they are not in an unchanged position from years together. What we have already thought it, they are stationary, they have the unchanged position years after years. So this concept was developed and they have started recognizing what is that, what is meant by motion of the planet, how it is taking place. Next comes here our Indian astronomers. So in 400 years back only, or 400 we can say that 400 later, after getting the interest from the many countries. So in the same period we can say that, or it is in the 5th century. So Indian astronomer, that is Aryabhatta, he said that the model which is celestial objects like planets, stars, they all are revolving around the sun there. Sun is a fixed point. But the interest got in another countries, or in many countries, they have suggested means they have got one idea that the celestial objects like stars and planets, they are revolving around the sun, not the sun. They are revolving around the earth. They present as the earth as a fixed central point, and in that stars. So let me consider this is a star that is also revolving around the earth here. And planets here. So they are also revolving around the earth. Right? So similarly, planets, celestial, we will say that earth, stars, planets, those all are revolving, or they are there in the sky, or they are there in a space. We will call it as a celestial objects like planets, stars and earth. So these are, we will call it as a celestial objects. They are revolving around the earth. So it is, we feel that they are in a motion. They said that earth will be the fixed central point. On that, stars and planets are revolving around it in a circular path, or we will say that it is in a circular motion there. Right. So this model was stated in stated by other countries scientists. We may say that it is a Copernicus, okay, and Nicholas these are the scientists who have got interested towards the planet's motion, and they have assumed or they have recognized as celestial objects like planets, stars. They are revolving around the earth in a fixed central point in a circular path. But later, some years ago, or 400 years after this recognition by the other scientists like Copernicus and Nicholas, they have said this model. And after this model, our Indian astronomers, that is Aryabhatta, suggested that it is not like that. All the celestial objects are revolving around the sun, not the earth as a fixed here. They have taken it as Aryabhatta has taken it as a, instead of earth they have taken sun. Sun has a fixed here around the sun. Star is revolving around the sun. Planet is revolving, okay, around the sun. Earth, okay, around the sun, earth. So around the sun, they have taken it as the sun as a fixed central point here on the circumference, or we can say that making center as the sun here. Planets, stars and earth also all are revolving in their fixed orbit in a revolution around the sun in a circular motion. The only concept is in the earlier scientists, means in this model we will call it as it is a geocentric model. Geocentric model it is, where fixed center is earth. Fixed center is the earth. As our Indian astronomers said, fixed central point as a sun here. On that, himself, sun, around the sun, earth, planets, stars are revolving around in a circular motion. Here also it is in a circular motion. Circular motion. All planets and stars all are revolving around the sun as a fixed point. That is heliocentric model. Where fixed point in a central is, or fixed center as a sun here. Right. So, basis of these two models, they have started again. Many scientists have started thinking over here. They spent a lifetime to recognize and observation the stars and planets, how they are taking the revolution, how they are taking the motion around the earth, or how they are taking the motion around the sun. They have just compared in a geocentric model and heliocentric model, and they have finally concluded that. So one of the conclusion scientists was that Tycho scientist. He suggested that finally they have given the definite model in which all the planets, all the celestial objects like the planets, stars, they are started revolving around the fixed center as a sun. So they had given the heliocentric model. So which is that all the celestial objects, planets, stars, earth are revolving around the fixed center as a sun in a circular motion. Later they have again started discussion, and they have recognized, and they had suggested that one more scientist, they gave the popular modification and in this heliocentric model it is. So that is one of the most important scientists was Galileo. He suggested out, he supported this heliocentric model. Yes, definitely all the planetary, all the celestial objects like planets, earths and stars, they are started revolving around the sun as a centrally fixed point, and means sun will be center there, where all the remaining planets or the stars started revolving around it in a circular motion there. Later, he gave the data, he gave recorded observation, he did the observation, he recognized, and he made it as a data. Later, he is one more scientist, Tycho. So that Tycho, what he did, he take out the help from the Galileo's data and he studied there. Later, he modified and he did some of the corrections in that. And later, after his data was extracted and studied in detail by his own scientist, that is Kepler. So Kepler was extracted the data what his sir or what his professor Tycho. So he extracted from that data and he gave the elegant laws there. 3 elegant laws he gave, that is law of periods, law of orbit, law of area. So these 3 are the elegant laws he extracted from his sir or professor Tycho. So scientists will say that it is a scientist Tycho. Later his discovery, later his recognition, later his definite prediction about the planetary motion. So those laws were named after him, that is the Kepler's law of planetary motion. This is very important topic, but this planetary motion and Kepler laws of planetary motions were not there for your NCERT syllabus, for board syllabus. But why I am explaining you this means this is very important as we move towards the competitive exams or the your JEE, NEET. These are very important topics. Without this understanding, we can't move or we can't touch the questions which is related to this part of the planetary motions. Right? So, what is that? We have 2 models in a planetary motion, that is the geocentric model and the heliocentric model. Geocentric model is the oldest one, where first the enthusiasm or recognition or interest developed in many countries of scientists. They have started thinking over that celestial objects are revolving around the one fixed point, that is they have taken it as the Earth here. So started planets, stars started revolving around the Earth in a circular motion. So sometimes or later, some years ago, our Indian astronomer, he first proposed that celestial objects are not revolving around the fixed point on the Earth. They have started revolving around the fixed point as a sun in a circular motion only. Again, some years later, so based on this heliocentric model, heliocentric means sun is the fixed center here, geocentric means Earth is the fixed. The remaining all planets, stars are revolving around the sun here. That is heliocentric model. This is suggested by the our Indian astronomers. Later, many scientists they have come over. Copernicus came. Polish smoke they have came. They have described and they have studied the deep observation about how the planets are revolving, how the planets are taking place, the motion. So they have started over that and they have predicted final model they have given. I mean to say that they have supported the planets and celestial objects are revolving around the sun in a circular orbit, not on the Earth here. So later one more scientist came, that is Galileo. Galileo first supported this heliocentric model, and later one more scientist, that is Tycho, he made the data, he observed and recognized, he shows us so much lifetime experiments he did for the observation of planetary motion, and he made the data, and this was completely recognized and analyzed by his own assistant, that is Kepler. So he, with the help of his professor's data, he extracted the elegant 3 laws, that is law of orbits, law of periods, law of areas. So on these 3 laws, he suggested how the planets are taking place the motion around the sun. That was the final prediction by Kepler's scientist Kepler here. So these 3 laws are named after him. Those are called as Kepler's law of planetary motion. Now we will study one by one. Kepler's laws of planetary motion. So we said now only, that is Kepler is a scientist. He extracted the 3 elegant laws from his professor's data, that is laws of orbit, laws of area and laws of periods. So one by one we will study how it is meant to be as a law of these 3 elements from the data set. So now let's move on to the laws of orbit here. So let us consider here, this is one of the elliptical path, right? So where in the laws of orbit, all planets are revolving around the sun here. So all planets are revolving around the sun in elliptical path here. In elliptical path, right? So all planets are revolving around the sun in elliptical path here, right? Now let me the point A and the point B have one particular That means here sun is there. S and S dash are the two foci. S and S dash are the two foci of the ellipse here. Right? So why I am saying the two foci of the ellipse means, if you consider the sun here, right? All the planets are revolving in the seems to be as a sea. This is the sun here. So planets are revolving around in a elliptical orbit. So planets are revolving around in a elliptical path. So complete elliptical path, S and S dash will be the two foci of the ellipse here. So two foci, they can take one side as a longer here, right? This will place the sun here, and if you place sun here, one place will be like this. So elliptical is completely in the form of this. So if you just take out here, either this will be the one of the foci, either this will be the one of the foci of ellipse. So I am taking it as a S dash and S here. They are the two foci of the ellipse. Now let's move to the exact diagram where we have drawn here. The point A is, see the distance of sun from this point. So this point where the sun is there, from distance from sun to the point A. A is what? That is the aphelion. That means far away from the sun it is. The point where the distance from the sun, the point where it is far away from the sun. If the planet is there in this position, what it will happen? Planet will move, or it will execute the elliptic path revolving around the sun, but it is far away from the sun. So what it will happen here in this position, or it is in this range? So planet will move very slowly. Its velocity will be decreases. Velocity is not so much to move faster here because it is very far away. This is the concept in laws of orbit here. So the planet which is moving, or it is showing the elliptical path around the sun, that planet, as you compare the distance from the sun, it is a far, that is called as aphelion. So when it is a far, it will do the path in a slower motion. So slow motion it is, slower it is, its speed is slow as its velocity is decreases. As once it is coming in this path, right, reach this, or it is the range which is very nearer to the sun. See, look at here, the point P where the distance from the sun, it is very near. At this position, what it will happen, or at this particular range, planet will move faster. So it will move very fast because it is very nearer to the sun. That point is called as a perihelion. So that perihelion, so aphelion means what? Far distance from the sun, its velocity decreases and it will move slower, right? Once the planet is in that range which is very nearer to the sun, it will move very fast. Its velocity is increases. So that is the main point here. The planet which is far away from the distance. So planet which is far away from the sun here, it will move slower, right? Its velocity is decreases. If the planet is in the range which is very nearer to the sun, right, where it has to take the elliptical path around the sun, it will move faster and its velocity will be increases. So this is what the laws of orbit tells, that in all the, in this law, all the planets will take a elliptical path. That is a special case it is. What Copernicus model said that the planet will revolving in a circular orbit, but as we consider the planets are taking their revolution around the sun, it is a completely elliptical path. So where we are having the two foci here. So we know the eccentricity of the ellipse. So what is that? Eccentricity of the ellipse. So OA, OS. So what is this? This part. OS by OA here. So OS by OA. So what is this OA? OA is nothing but the A here, the distance from the center of the ellipse here. Right? So what it will happen? OE, OS by OE is E. So E is there here. OS is equal to E into A here. So that will give you the eccentricity of the eclipse here, right? So eccentricity of the eclipse. So this will tell us about the, so you have studied already what is eclipse, the hyperbola, parabola. So all these things we have studied in mathematics part there. But even though I'm just clarifying here, you should know eccentricity. Eccentricity means what here? The distance of a sun from the elliptical path. And OA is what? The center of the eclipse. Where the point, where the planet, it is far away from the distance of, or from the point R, sun here, where it has to take a slower, its speed is very slow compared to the point where it is very nearer to the sun here. OAS means what here? This is the exact position. O dash means what? The one of the foci of the eclipse, it is very nearer to the another point test, right? OS will tells the, if the sun is there in this position, what will be the path of the planetary? So it will be very nearer. It is a fast here. The sun is not here. Sun is there in this another foci of the ellipse. So we will take it as a OA divided by OA here. OS divided by OA. OA means what? The distance of center of the eclipse to the point where it is far away from the distance of sun. So it will take the slower path there. So that is eccentricity is equal to OS by OA is equal to OS. OA is the what? A here. So OS is equal to E into A. So this will give you a very important clarification of how the planetary motions will take place in a given questions there. They will ask how the elliptical path taken by the planet, how much it is. If you know the value of OS and A, you can substitute and find out the eccentricity. That will give you the laws of orbit or the elliptical path of the planet here. This is about the our law of orbit. So to understand this law of orbit, I will give you one example. How means, if you just take the one pencil here. So if you just take the one pencil here, right? So what it will be, again I will consider this one. Right? So these 2 points will be foci of the ellipse, right? In case of circle, what it will happen? These 2 foci will be merged. So and it will become one center there. So these 2 foci will be merged. In case of circle I am discussing. In case of circular path, the 2 foci will become merged to each other and becomes the center of the circle. And semi-major axis will becomes the radius of the circle here. You should understand this. What is the difference between the circular path and what is the difference between the elliptical path here? Elliptical path we have a 2 foci. 2 foci means it will be in an enlarged portion. It is not an equal distance as we have mentioned. The distance from the center to any point on the circumference when the planet is executing the circular motion there, right? So that only I am discussing here. If the 2 foci are there in ellipse or ellipse, right, in elliptical path, these 2 foci are merged in case of circular path of the planetary motions becomes the center of the circle, and semi-major axis or the, we can say that the distance, right, it will play the role of radius of the circle. So in laws of orbits, what Copernicus model said that the planet should move in a circular path, not in the elliptical path. So but all the planets are executing the elliptical path means it's a special case of that planets. It's exactly taking the elliptical path where it is having the 2 foci here. To understand this concept, so I have given here one pencil which is placed here on any point of the elliptical path. So if you take this S dash as a F dash here and S as a F here, to understand purpose, instead of taking sun I have taken the 2 foci of the pencil T here. So foci of the pencil T here. The distance TF1. So TF1 is equal to TF2 here, right? So let me take it as a F2. So distance from the pencil to F1 and distance from pencil to F2. So these 2 are again the foci of the eclipse here. So this will be constant throughout the elliptical path. Wherever you can take the pencil on the circumference of the eclipse. So this will be remains constant here. So it is moving. It is moving at this point means it is very near at this point. So this will be the one of the distance here. So sun, the point where it is moving the elliptical path. So F dash here, and F2 is a one more distance from the pencil here on the same elliptical path here. The distance from the pencil point to the one of the foci and the distance of pencil to the another foci of the ellipse, that distance will remain constant. So in this constant, that is the concept here, the law of orbit. So distance from the circumference of the ellipse of any foci or any one of the foci of ellipse will be with compared to the distance of any another foci of the ellipse will be remains constant. So this is about the law of orbit. So next we move towards the law of area. In this law, any planets revolving around the sun or swipes around the sun equal area in equal intervals of time. So let us consider here, I have drawn again one elliptical path. So this will place the role of sun here. So if it is a sun is one of the foci of the ellipse here, what it will do? The planet, if it is at the point of A, so it will move towards with the velocity v here, right? So it is moved towards with the velocity v and reaches to the point B here. So the planet swipes around the sun equal area in equal intervals of time. That means what? If it just take the path from the planet, if it is at the point A, it will move towards the point B with the velocity. Velocity means what here? It's a far away from the distance of the sun, so it will move slower. It is observed from that model where the planet is far away from the distance of sun, it will move slower and its velocity is decreases, right? It will cover some area here. So when it is moving towards the point which is nearer to the sun, its velocity increases and it will move very faster as compared to the speed or the velocity where it is far away from the distance of sun here. So we are studying the law of area on the concept of the velocities of the planet which executes the elliptical path around the sun here. So instead of saying elliptical path of around the sun, we will just use the word swipe. Swipes around the sun equal area in equal intervals of time. So similarly, if it the planet is there here, so it will comes at the point C and covers the D, or else we can say that the planet is there here at the point D and it will cover the C part in the same equal area in equal intervals of time. So to understand this, so I will draw one more diagram here, right? So let us consider this is the center of the elliptical path, right? So if you just move here A, so B here. So let me consider here only C and let me consider here only the D here. So let me consider here sun. So center, I will just explanation part, I will take it here sun. So sun will be here only. So the planet is moving in this direction. So when planet is there in this point, so it will move towards B here, right? And planet is there in the path of B here and it will move towards B and it will come to this part. So how much area is there here? The equal area in equal intervals of time. The planet is moving at the point A with the velocity v here and reaches to point B, right? And that the equal area, this planet is moving from A to B in a particular small intervals of time, that is equal to the planet if it is there at the point C and moving towards this D. The same equal intervals of time it will complete. That is the meaning of law of area here. See, look at here. It is based on the study of, so planet is far away from the sun, it will move slower. As the planet is very nearer to the sun, it will move faster. It is depending upon the velocity of the planet which executes the motion, planetary motion. If it is far, it will move slower. Velocity decreases. If it is far from the distance of sun, it will move very slowly. If it is nearer to the sun, it will move faster. Its velocity is increases. Similarly, the area ASB is equal to area under C area. So on which basis the law of area we are discussing? With the help of that is velocity of the planet which executes the elliptical path, which is far away from the sun, it will move slower, means velocity decreases there. If the planet is very nearer to the sun, so its velocity increases and it will move very faster compared to the when it is velocity of the planet far away from the sun here. So based on this, the area under means area of the planet covers or swipes equal area in equal intervals of time. That's only equal intervals of time. That only we have discussed here. The area under ASB is equal to area under CSD. So angular momentum. What is the angular momentum here? mv1r1. So that is of moving. Angular momentum of a planetary from A to B it is. So angular momentum of planet C to D. From C to D and A to B. So mv to r2 here. So mass means same planet only it is moving. No. So it will be equal here. v1 r1 is equal to v2 r2 here. So Vr will be remains constant here. V remains constant. Velocity and the distance from the sun it will remain constant. V velocity. So it is a far slow velocity. It is a near fast velocity. Fast velocity means velocity increases. Velocity decreases when it is far from the sun. Velocity increases when it is nearer to the sun. That only we have discussed here, aphelion and the perihelion, right? This is about the law of orbits. Now we will discuss about the law of periods. So time taken by the planet to complete the revolution here. So in the last topic we have discussed time period of the satellite, that is square of the time period of the satellite is directly proportional to the cube of the orbital radius. So at that time I have mentioned this is nothing but the Kepler law of planetary motion, the second law of planetary motion, right? Now we will move towards the laws of periods as we have discussed here, law of orbit, law of area. Now next the last element law of the Kepler's law of planetary motion, that is the law of periods. So that is time taken to complete the planet in a elliptical path. So that is what? Square of the time period of the planetary or a planet is directly proportional to the cube of your semi-major axis of the elliptical path. So let us move on to with the help of this diagram only. So what is this? This is nothing but the semi-major axis of the elliptical path here. If you consider the time period of the planet T1 here, then its semi-major axis will be R1, right? So if you consider the time period of the planet, that is the T2, its semi-major axis will be R2. What the law suggests here? Square of the time period of the planet is directly proportional to the cube of the semi-major axis of the elliptical path. So we have discussed in a previous topic where we got the time period of the satellite. So that is what? Square of the time period of the satellite is directly proportional to the cube of the orbital satellite here. I mean orbital radius. So there I have mentioned it is a Kepler's second law of planetary motion, right? Here we are just discussing what is that the law of periods states here. So that means time taken by the planet to complete the revolution here, that is totally depending upon the semi-major axis of the elliptical path where the planet is executing the elliptical path around the sun here. So if you consider T1 and T2 here, its semi-major axis will be R1 and R2. So as it is said, as square of the time period of the planet is directly proportional to the cube of the semi-major axis of the elliptical path here. Now if you consider T1 and T2 whole square here, then what it will happen? R1 and R2. So this is of R2. With the help of this law of periods, they may ask your competitive questions also based on this. So I have a cross check here. With the help of law of periods only we can solve the many problems which is related to the law of periods here. Just remember this from your T1 by T2 is equal to R1 square, sorry, T1 T2 whole square is equal to R1 R2 by whole cube. That tells here square of the time period of the planet, that is directly proportional to the cube of the semi-major axis of the elliptical path. Or else we can say, when we taken it as a satellite, we can say that square of the time period of the satellite is directly proportional to the cube of the orbital, radius of the orbit, or the orbital radius. So this is all about the Kepler's law of planetary motions. So with the help of this, we can able to recognize how the planet is revolving around the sun, or how it is taken. These are the history that we have discussed. The more important, interesting topic is how it is developed. So these all we have discussed. So as I mentioned in the beginning only, to discuss Kepler's law of planetary motion, this is not there for your NCERT syllabus or for your board syllabus. But as a synopsis we have taken, as we have considered this topic is very important as you move towards the competitive questions. Unless and until you have not understood this topic, you won't solve the related to this topic problems. So I have planned to discuss, and I think I tried my level best to reach what is these laws suggest. Second law, that is the law of periods, we have already discussed at the time of satellite time period discussion was going on. And the law of area is also very simple, that is angular momentum based on the velocity of that is we have discussed. So only thing that what is law of periods suggest, what is law of area suggest, what is law of orbit suggest. Once you know this one, with the help of this concept you can apply in solving the competitive questions here. So this is very clear that you should know whether it is there in the syllabus or it is not in the concerned syllabus part. At least you have knowledge, means you can just apply on it and you can go ahead with the solution of the competitive exams. So for the competitive exams, you should not consider it as a restricted syllabus, it is a restricted portion. It is for the NCERT syllabus, what is there that we have to study, what is not there, it is not to be so important given to that. So similarly, once we know the concept as a part of your competitive, if you go through this class and you can clarify your confusions, then you can go ahead with the NCERT also. In that textbook they have given in a short there. Even though I have a little tried my level best to understand you the Kepler's law of planetary motion. This problem here, the mean distance of mass from the sun is 1.524 times that of the earth from the sun, and find the number of years required for the mass to make one revolution about the sun. So what is T1 is what? Time mass, time period, right? So that only we are going to find out here. We don't know how much it is, right? So T2 is what here? It's a time period of the earth here. So what is, they have given 1 year time period of the earth. So that is 1 year they have given. Then R1 radius also they have given 1.24, right? So now with the help of this law, what is that? T square directly proportional to the cube of the, that is the radius there, right? So T1 T2 raised to 2, that is equal to R1 R2 cube. So we don't know this T1 T2 here, right? So R1 R2 raised to 3 by 2 here. So I will take T1, so because square it will go means 3 by 2 it is. Then T2 R1 by R2 3 by 2 here. This R1 and R2 with the help of that is given that of earth it is. So we will take it, T1 is 1 year here, right? So 1.524 3 by 2. So what we will get here? 1.88 years. So that is the time period of the mass here, what they have calculated, told to calculate here to make a one revolution about the sun. So how many number of years is required for the mass to complete one revolution about the sun? That is of 1.88 years. So like this, if such kind of problem is there, you can make use of the law of periods here and find out the solution, right? we'll go for the next problem. We'll solve some numerical problems here. What is that? Find the relation between the gravitational field on the surface of the two planets A and B. The masses Ma and Mb are the same two planets here, and the radii are A and Rb respectively. Means masses of the two planets A and B, they are having Ma and Mb here, and they have given Ra and Rb as a radii of the same two planets. If they have the equal masses and if they have two equal density here, or else we can say that it is a uniform density. Uniform density. Let us move on to the solution of this question here. The two planets A and B are on the surface of the Earth. On the surface of Earth here. Okay. So, if the two planets are there on the surface of the Earth, we need to find out the relation between the gravitational field on the surface of two planets first. So, that is A and B here. And their masses Ma and B, Mb are given here, and Ra and Rb are the radiuses of the again two planets given here. Only one thing is that two options they are given. If they have equal masses and if they have equal density, one by one we will go to solve here. Then Ma and Mb are the masses of the two planets here. Masses of two planets A and B here, right? And Ra and Rb are the radius, or we can say that the radii of two planets here, right? So two planets A and B here. So we know that the gravitational intensity of gravitational field on the surface of the Earth. What is that? We'll see here. Gravitational field or intensity of gravitational field. Intensity of gravitational field on the surface of the Earth. If any planet or a body on the surface of the Earth, we see here. So what is that? We have discussed in a previous class that E is equal to Gm by R square. We have calculated, right? So gravitational field or the intensity of gravitational field on the surface of the Earth is this one. So once we have this one, the already two planets we have considered on the surface of the Earth, then obviously it has to execute the gravitational field on these two planets. Now let us go ahead with the intensity of gravitational field on planet A. Then what we will get? Gm by Ra square, right? So for the planet A it is. For this planet A. So intensity of gravitational field on planet A on the surface of the Earth here. Then what about planet B? So planet B, E. B is equal to Gm by Rb square here. Now we have to find out the relation between the intentional or the gravitational field on these two planets here on the surface of the Earth. Now we have Ea, you got it? Eb is also got. What is these two? These two are the intensity of gravitational field of a two planets A and B. That we know. Then we'll take it here. Ea by Eb. What will have? Gm, right? Gm by Ra square here. Then I will take it here directly. Rb upward here. Rb square by Gm. Can I do it or not? Yes. Now what it will happen? It will cancel and remains with the Rb square by Ra square. So what is this? This is of first part when they have equal masses there. And when we have equal masses, both the planets have their same masses, then what will be the gravitational field on the two planets on the surface of the Earth? So this is of the Ea, intensity of gravitational field on planet A by intensity of gravitational field on planet B, and their radius, ratio of the square of the radius of the planets. So this will give you the first part, right? So this will give you when they have a equal masses there. Now we'll move towards the when they have a equal density there. So what is density here? And just edit this one. So once they have a uniform density. Now again take the help of this. So EA is equal to Gm by r square. This is our intentional gravitational field on the surface of the earth. That we know what is the gravitational field of a planet A and a planet B on the surface of the earth. So that is nothing but the intensity of gravitational field of a planet on the surface of the earth. Once we have a mass. So how it is the mass of the planet? If you go ahead with the density of a mass. What is the density of mass? Density of masses of the planet. So generally we have 4 by 3 pi 4 by 3 pi r cube rho it is. Then what about the mass Ma? 4 by 3 pi Ra cube rho a it is, right? And what about the planet B here? 4 by 3 pi Rb whole square rho b. So once in first case what it is happened? Equal masses. In second case what is that? Uniform density rho a and rho b. These are the densities of the rho is what? Mass of the density of the two planets. When they have uniform, then what will be the gravitational field on these two planets, right? Now what is it? EA. Right? EA means what here? Take out. In place of M, place the value of mass of the first planet. So G, M is what? 4 by 3 pi Ra cube of rho A it is. Right? So rho A will take it outside only because it is uniform. Right? What is remained here? So not the denominator here. This is the gravitational field. Right? First part. And gravitational field. So G 4 by 3, second one it is 4 by 3 by R B whole cube, right? So whole cube it is, second part. Now go ahead with the ratio of gravitational field. So EA by EB, what will happen? Place here G 4 by 3 pi R cube A, right? So what is that? So divided by R A square, right? Now G 4 by 3 pi R B cube of R B square here, right? So because this directly I have taken EA is what here, so sorry I have to write it here R A square. So here R B square, right? So what it will happen? Directly I have right here. Only thing that this one and this one will get cancelled. This one and this one will get cancelled. Ra cube is there. Ra square is there for on EA there. Similarly, EB, RB is cancels each other. What is remaining here? G 4 by 3 pi Ra. Right? So G 4 by 3 pi RB here. So these all are remains constant. G, right? 4 by 3 pi. These are the constants. What is remain here? Only thing that Ra by Rb here, right? So EA, ratio of their gravitational field, if they have a uniform density, then you will get, see here, EA, ratio of gravitational field, EA by EB is equal to Ra. What is this? This one will remain constant. If you have cancelled also, they will get cancelled. What is remain here? Ra by Rb. That is the nothing but the if they have a equal density, the gravitational field on the surface of the two planets A and B, if they are on the surface of the Earth here. So this is nothing but the solution of this problem. What they have asked, if they have equal masses, what will be the gravitational field, and if they have equal density, what will be the gravitational field? That is the relation between gravitational field on the surface of the planets A and B. The masses they have given, radii also they have given. So
So what will be the solution? This is the way you need to go ahead with the density, how they are uniformly equal to each other, and what will be the intensity of gravitational field. And when they having the equal masses, what will be the intensity of gravitational field on again two planets. Find the value of G on its surface, as the gravitational constant value is also given here, 6.67 into 10 to the power minus 11 Newton meter square per kg square here, and also find the mass of the earth. So first, before solving this one, very important things is what are the things is given, what is the given task to find out the in the problem here. What is that? First we need to find out the value of acceleration due to gravity. Rest small g value it is. Gravitational constant value already they have given. The thing whatever the given data is here, radius of the sphere means earth. Earth is in the form of uniform sphere. Its radius is also given and density is also given. With the help of these two, we can able to find out the acceleration due to gravity. That is small g. So let us find out what is the given data here. Radius 6,400 kilometer here. It is in terms of kilometer. Let us convert it into meter here. That is 6.4 into 10 to the power 6 meter here. Right. So again what they have given? Density 5.5 gram per cc they had given. You just convert it in terms of kg here. That is 5.5 into 10 to the power 3 kg per meter cube here. Now what is the next process here? We need to find out the small g here, right? So we have acceleration due to gravity on the surface of the earth. What is that? G is equal to gm by r square here, right? The thing is they had given density of the mass here of the earth here. So density they had given. So given with the help of given value, the mass is what? 4 by 3 pi r cube rho it is, right? In place of G, capital N, G n by r square they have given. No, in place of M, with the help of density we are going to place here G 4 by 3 pi r cube rho it is, right? So divided by r square. So divided by r square. Here r and r will get cancelled. What is given here? G 4 by 3 pi r rho here, right? So g value they had given. What is that? 6.67 into 10 to the power minus 11, right? Into 4 by 3 pi value 22 by 7. Yes. Next r value. R value is what? 6.4 into 10 to the power 6. Rho value is what? 5.5 into 10 to the power 3 here. So what the value you get it by doing all these things? Approximately you can do by yourself 9.8 meter per second square here, right? You just pause it and do it by yourself whether you are getting the same value or not, right? So once we got the acceleration due to gravity small g value here, now we will move towards the finding the mass of the earth here. So mass of the earth, again with the help of acceleration due to gravity, so gm by r square here. You just bring it here, gr square is equal to gm here. So what do you need to do here? Mass, no, gr square by g. So you will get the mass of it. G you know, r they had given, capital G, the gravitational constant they had given. So only thing that we need to find out the mass here. So what is that? M is equal to small g is a 9.8, right? Into r 6.4 into 10 to the power 6 whole square. It is then divided by 6.67 into 10 to the power minus 11. So 6.018 into 10 to the power 24 kg. So this is how we have to solve the problem. If you are not getting a clear idea, you can just draw the diagram. With the help of diagram, you can solve the problem also. Right? So here they are asking how much above the surface of the earth does the acceleration due to gravity reduces by 36% of its value on the surface of the earth. That means acceleration due to gravity on the surface of earth, it is 100%, right? It is maximum it is. So if 36 percentage of acceleration due to gravity is reduced. Reduced means height is there. The person or the body which is above the surface of the earth, there the acceleration due to gravity 30% is reduced. Means reduce the acceleration due to gravity on the surface of earth. How much it is? That much 36% it is reduced. Now what they have to given the task here to calculate here, 36% of its value on the surface of the earth, right? We need to find out the how much height, how much above the surface of the earth goes the 36% reduces with the value of the acceleration due to gravity on the surface of the earth. Now what are the given here? Go for the solution here, right? So 36% reduces. So reduces the acceleration due to gravity here, right? So we need to find out the height here. Now we have acceleration due to gravity. Acceleration due to gravity on the surface of the earth. Acceleration due to gravity on the surface of the earth. On the surface of the earth is how much here? We'll go ahead with the 100%. Right? Now it has to reduce here 36%. That means what we need to do here? Minus 36. Right? So what is happening here? 64. That means 64%. Right? If you detect here 100% on the surface of the earth, so what they are asking? 36% it is reduced. So 36, how much it is remained? 46% is remained. Right? So 36% is there. Only 36% is reduced. 36% it is. So 36% reduces. Then we need to find out reduces the acceleration. Here we need to find out the height. How much height we have to calculate where the 36% is there. So acceleration due to gravity on the surface of the earth is 100% here. So 100 minus 36, that is 64 here. So 64% it is. That is nothing but the G dash here. So G dash is equal to 64% of G meters. So 64% is also we can write it here 64 by 100 of G here. So now we have according to the height, in which height above the surface of the earth execute the acceleration due to gravity. So what is that? G of r square divided by r plus whole square here. Right? So G dash value how much it is? 64 by 100 of G here. So G of r square divided by r plus h whole square. So G will get cancels, remains with 64 by 100 here. That is r square r plus h whole square here. So look at here, both the sides r square is there. I will just take out to this side, means root of 64 by 100. So what is remaining here? R by r plus h it is. So root of 64 is 8, root of 100 is 10 here. So r by r plus h here. So cross multiplication, 8 of r plus h is equal to 10 of r here. So what you will get? 8r plus 8h is equal to 10r here. So r, what is it? 8h is equal to 10r minus 8r here. So what we get? 8h is equal to 2r. So h means what? 2r by 8 here. So what is the value? So 1 by 4 r here. So 1 by 4 r they have given r is equal to what here? 6400 kilometer. So in terms of meter, what it is? 6.4 into 10 to the power 6 meter it is. Right? Now h is equal to 6.4 into 10 to the power 6 divided by 4. So you will get 1.6 into 10 to the power 6 meter. So this is the expected value, or this is the expected height where its acceleration due to gravity 36% reduces with the compare of acceleration due to gravity on the surface of the